All right, let's break down one of the most important inventions in human history, the transistor. It's the silent, invisible engine of our entire digital world. And today, we're going to get right into how it actually works. Take a look at this number, 50 billion. I mean, just try to wrap your head around that. It's an enormous number, and it's the number of tiny, tiny electronic switches that are packed inside just one single AI chip. And these aren't just sitting there. They're flicking on and off billions of times every single second, all in a piece of silicon smaller than your fingernail. The scale is just, it's honestly mind-boggling. So that brings us to the big question, right? How on earth does a switch that small even work? What's really happening down there at that microscopic level? Well, let's dig in. Okay, so the first thing you gotta get is that all this incredible complexity, it really just boils down to one super simple idea. A transistor isn't magic. At its heart, it's just a switch. It does one of two things. It either lets electricity pass through, or it stops it. That's it. And believe it or not, that simple choice, on or off, that is everything. See, when that switch is on, letting current flow, we call that a 1. And when it's off, blocking that flow, well, that's our 0. Every photo you take, every song you stream, every single thing your computer does is just built from endless strings of these ones and zeros, all controlled by billions of these tiny switches. Okay, so how do you actually build a switch this elegant? Well, the secret ingredient is a special kind of material called a semiconductor. And when it comes to semiconductors, silicon is the undisputed king. You know, the name kind of gives it away. It doesn't conduct electricity great, but it doesn't block it completely either. It's in between. And that special property, that's the whole key. This is where things get really clever. We take plain old silicon and we basically give it superpowers through a process called doping. We intentionally mix in tiny, tiny amounts of other elements. If we add one kind, we end up with a bunch of extra free-floating electrons. Since electrons are negative, we call this N-type silicon. And if we add a different kind of impurity, we create a shortage of electrons, leaving behind these little gaps that we call holes, and we call that P-type silicon. So this ability to engineer these little zones with either too many electrons or not enough of them, that is the fundamental trick. It's what lets us create these little pathways and roadblocks for electricity, and it's exactly how we're going to build our electronic switch. All right, to really get a gut feel for this, let's use an analogy. So forget about electrons in silicon for just a minute. I want you to picture a simple water faucet. Honestly, it's the perfect way to think about how a transistor controls the flow of electricity. So let's break it down. The pipe where the water comes from? In our transistor, that's the source. The spout, where the water pours out, that's the drain. And the handle, the most important part, the thing you turn to control it all, that's our gate. Source, drain, and gate. Remember those three. Okay, so how do we turn on our electric faucet? Simple. We apply just a tiny bit of positive voltage to the gate. That's literally like turning the handle. Now, what this does is pretty amazing. That voltage creates an electric field that forms a temporary little bridge, a channel, for electrons to cross. And just like that, there's a path. And boom, the electrons start flowing from the source to the drain. Our switch is now on. And turning it off? You guessed it, it's just as easy. You just remove that voltage from the gate. The electric field collapses, that little channel disappears, the path is gone, and the electrons stop flowing. The switch is now off. It's really that elegant. A tiny little charge on the gate is controlling a much bigger flow of current. That's the magic. Okay, so we've got one tiny switch figured out. That's awesome. But, you know, one switch isn't going to get you very far. The real magic, the power, comes from what you can do when you start wiring billions of these things together. So the first step up is to combine just a handful of transistors to build something called a logic gate. Think of these as super basic decision makers. Like, an AND gate will only spit out a 1 if both of its inputs are also a 1. These gates, they're the fundamental Lego bricks of all computation. And then we just keep building. We take those logic gates and we hook them together by thousands, even millions, to build bigger, more complex blocks. You know, things you've actually heard of, like memory for storing stuff, or the parts of a processor that do all the math. And just to put this into perspective, want to store a single bit of information, just 1 1 or 1 0, in the fastest kind of memory your computer has, what's called SRAM, that takes 6 of these transistors. 6, just to hold one tiny bit of data. So when you put billions, and I do mean billions of these little building blocks together on one chip, well, that's how you get the powerful brain inside your phone, your computer, and those giant AI chips that run the cloud. It all scales up from that one simple switch. So for decades, right, the whole game has been about one thing: shrink. Make the transistor smaller, you can pack more onto a chip, and that makes it faster and more powerful. Easy. But we're getting so small now, we're literally bumping up against the laws of physics, and that's creating some huge problems. See, as these switches get smaller and smaller, things get weird. When a switch is supposed to be off, it's not always fully off. Some electrons can actually just tunnel right through the barrier. It's a bizarre quantum effect, and that creates a leak. Plus, you cram billions of these things together and they generate a ton of heat. It's a massive challenge just to keep them from melting. So what did the engineers do? They got clever. They went 3D. The old school transistors were flat. The gate just sat on top of the channel, kind of like a bridge over a river. But as things got smaller, its control got pretty sloppy. The modern solution is called a FinFET. Instead of being flat, there's a little fin of silicon that sticks up, and the gate actually wraps around it on 3 sides. This gives the gate way better control over that channel, and it helps clamp down on those annoying leaks. I mean, this shift to a 3D design was an absolute game changer. It's the reason we've been able to keep making computers faster and more powerful. But even this has its limits. And figuring out what comes next, that is one of the biggest questions in all of science right now. So here's the bottom line. From one simple on or off switch made by just cleverly tweaking a piece of silicon, we've built our entire digital world. It is, without a doubt, the single most important invention of the modern era. And that just leaves us with this one huge, fascinating question. Now that we're pushing up against the absolute physical limits of silicon, what comes next? What new materials, what crazy new designs, or what completely new kinds of switches are going to power the technology of the future, your future?